Now, we need to guess the structure of our data sequence, the solution data sequence. And from our Tower of Hanoi problem, we know the structure of the solution data, right? 2n minus 1. That minus 1, a little annoying, right? Yeah, but we know the dominant part is the 2 to the n. So it is a exponential function. 2 power of some number. That structure. All right. Can we imagine? We need to, based on our understanding of the problem, can we make a guess? Our solution data sequence should have the similar structure, make this kind of connection. First order, second order, at least they should share some similarity, right? So that's our understanding. Our understanding is very flexible. What's the understanding? So you can think about what is human understanding. Human understanding, basically, you need to find some good reason when you want to do something. If you can find a good reason, then you can try to do things in that way. Here, we find some good reason, good connection. The connection is this Tower of Hanoi problem, because they are similar problems. Can we imagine the similar problems should share similar structures in their solution data? That's our understanding part. Okay? Yeah. So if we have that part of understanding, then our guess, our structure guess is the solution data sequence should have this structure. Power of t. Yeah. What is t? T is some number. T is some variable. The value of t can change. We have freedom to choose appropriate t. We have freedom to choose appropriate t. But we want the whole data sequence. We want to try. At least we want to try. If we use this special structure, power of t structure, can we find a solution in this structure? Let us do some testing. All right? So let us assume a sub k equals t to the kth. Then we plug in and see if we can get a solution. All right. Yeah. And this sequence we know, geometric sequence. Yeah. All right. So this simple sequence, now we want to see if we can find a solution in this simple sequence. All right. Yeah. Yeah. Some people may worry about initial condition. Some people may worry about initial condition. So when you make that assumption, structure guess, how can you make it satisfy the initial condition? Right? Yeah. It is hard. Initial condition will, discourage us to go along this solution path discourage us. So let us temporarily ignore the initial condition. Don't worry about initial condition. Later we can add it back. Okay? Here we only target the recurrence relation part. That's the major part. We target the major part. The initial condition part, that's the minor part. So we leave it out, the minor part. All right, so based on this understanding, now we can do the work. Okay, yeah. All right. So let us plug in. Straightforward plug in. So you get a very simple equation, right? Yeah. So then you do simplification, cancellation. So what you get is a simple quadratic equation. T squared equals t plus 1. That quadratic equation we are familiar with quite a lot, right? Yeah. The golden ratio. You can see this quadratic equation corresponds to the golden ratio directly. Yeah. Solution. Yeah. So we solve this two solutions. T1, 1 plus root 5 over 2. T2, 1 minus root 5 over 2. We apply quadratic formula, so we get two solutions. Yeah. The first one we know it's golden ratio, right? Yeah. The first one is golden ratio. Yeah. The second one is not. Second one is not. The second one is a negative number. The negative number. So here the question is, we know the second one is a negative number. Less than 0. The question, should we drop the negative answer, negative root? We keep the positive root, we drop the negative root? That question. When we calculate the golden ratio, remember, when we solve that original quadratic equation, we drop the negative value of that equation. But that situation is different from this situation. Our current situation is different from the situation that we calculate the golden ratio. Because that ratio we know, when we define the ratio, it must be a positive integer. Oh, not integer, positive number, not integer. When we define that ratio, its meaning is the ratio of the lengths of two line segments. That must be positive. But here, what is this t here? The meaning here, it's not necessarily the ratio, right? T, just any number. We only need a t, some number. Okay? Yeah, some number. Yeah. Okay. Although, usually we work on the real numbers, right? Yeah. Usually we work on the real numbers. Oh. By that. Yeah. Real numbers. But here, we do not even require real numbers, just numbers. Valid numbers. Okay? Valid numbers. Because if it is, even if it is a complex number, it is still okay. If it is a valid number, we can put there. Okay? So for that understanding, that's another understanding point. For that understanding, we should not drop T2, negative solution. We keep it. Right? So this step, we find two t values that can make the the sequence structure fit. Yeah. So we want to use sequence structure to fit our target data. Our target data is a sequence of data. Now, we get something. Okay? Two possible sequence data. Two sequences. Two possible data sequences that can fit our target data sequence. But there are two, not one. There are two candidates that can be used to represent our target data sequence. All right, next step. This time, now we need to make connection. Because we don't know if we get garbage, right? Two strange numbers, T1, T2. They are two strange numbers, right? Yeah. Many people, after they see root of 5 fraction thing, they drop them. Yeah. They give up. They feel this path won't work. So they drop this possible solution path. Okay? Yeah. Not reasonable, but actually it's not useless. So these two numbers, not garbage. These two numbers, still useful. All right? Yeah. So let's continue our story. Yeah. Now we go back. So here, let's plug in these two numbers back to our original equation, on the original recurrence relation. Yeah, so this is our original equation. We plug in T1. It must be true, no problem, right? Yeah. This first equality must hold. Second, even the negative number in the base part, the base number is a negative number. But our exponent is an integer, right? Our exponent is an integer. So the base number is negative, but when we do integer number power function, still we can calculate it. So the second equality also holds all the time for all non-negative exponent numbers. Always true. Both equalities are always true. That's for sure, right? Yeah. Although they are not integers, here many people worry about these two base numbers are not integers. It's true, not integers. But can we use these numbers to get integers? That's another question, right? So these two base numbers, originally they are not integers. But can we use some special way to combine these numbers so that we can get integers? That's another question, right? Yeah. That's another question. All right. So the next step, this time, one problem initial condition, because these two equalities, these two sequences, another technical problem they are not satisfying the initial condition. They do not satisfy it. the initial condition. They do not satisfy. All right, but although they do not satisfy the initial condition, but we do not use these two data sequences as our final solutions directly, right? So we have these two candidates to represent two candidate sequences to represent our data solution data sequence. Yeah. All right? Yeah. Or we can treat as two generators to generate our solution data. Okay? Yeah. These two sequences, we treat them as the generators to the purpose to use these two generators. We want to form our solution data. That's the purpose of these two sequences. That's another view. That's another understanding. Another level of understanding. Okay? If we can combine them, combine these two objects, we use them as generators. Then our goal, we want to generate our original data sequence. So that's another level of understanding. Okay? Yeah. No problem to think in that way, right? No problem to think in that way. But next question, another important question. How to generate the data. How to generate the data. Okay? Yeah. Now we agree. Yeah. That's fine. You can go along this solution path. You can try. But you need to solve another technical problem. How to use these two objects as two generators to write the formula for your solution data sequence. That problem. If you can answer, you can find a reasonable way to do it, then we are very close to the final destination. All right, here, there is one simple way people can use in this situation. All right, let's recall, look at the name of this recurrence relation, linear recurrence. All right, here the key word is linear. This key word is very useful. This keyword tells us there is some convenient property we can take advantage of. The property we call the linearity property. Linearity property. So here, we want to combine the linearity property, but not combine. So we want to apply this linearity property to combine these two objects to form our solution data sequence. That's the idea, the linearity property. What's the linearity property? So that next question. So what's the linearity property? Okay, all right. another concept. Another concept. To get a new solution. The new solution. Because if we have freedom, so here, initial condition. Don't worry. After we get a representation for the new solution, if we have some freedom, we can apply our freedom to fix the initial condition part. So that part. But the question is, we need to represent our new solution. All right? Yeah. Right. Let's do the part. Here, let me explore that linearity property here. Okay? Linearity property tells us you have two objects. Okay? Yeah. So here you have two objects. Two, let's say, solution objects. Our two objects are two solutions. Two solution objects. When you have two solution objects, you want to represent as a general solution object. General solution object. Yeah. You can use a special way called a linear combination way of two objects. Yeah. Here I use two variables, x and y. Concrete objects, but we can replace x variable, y variable by other mathematical objects. Okay? Yeah. All right. Linear combination of two variables, that means this structure. Constant capital A times x plus constant capital B times y. This structure, sum of these two numbers, we call the linear combination of A, x, and y. That concept. Okay? Linear combination concept. Linear combination structure, when we use this structure on our solutions, on our two solution objects, we have two solution objects, right? Can we apply linear combination operation on our two solution objects? And we want to make it our new general solution objects. That's our understanding in our mind. That's the understanding in our mind. Okay? Yeah. All right. So now we do our work along this understanding. All right. So here, capital A, capital B, they could be arbitrary constant. That's the freedom we have. Arbitrary constant, we use them as two freedoms in our final solution. Freedoms are important in our final solutions. Yeah. So let's keep those capital A, capital B. All right. Now, let me show you the logic behind this linearity property. How do we apply linearity property? All right. We have two solution objects. Then we apply linear combination of two solution objects. So we replace two variables by two solution objects. Okay? Yeah. No problem. So we get another solution object. Okay? All right. Yeah. New form of the solution, A times the first solution object plus B times second solution object. That's the linear combination form of two solutions. And here we want to say this whole expression is also a solution. Can you see it? Can you plug into our original recurrence equation and see if it also satisfies the recurrence relation? Yes. Yeah. You can see easily by the linear radial property, because by the linear recurrence, homogeneous linear. Okay? Yeah. But if not, if it's not linear, yeah, let's say this one. If it's not linear, you cannot do this. Yeah. If it's not linear, okay? For example, if you have equation fn squared equals fn n minus 1 squared plus fn minus 2 squared, this is not a linear. Okay. Then, suppose you find two solution objects, right? Object, one object. Then you do linear combination, then you plug in. No. So your linear combination of two solution objects won't be a new solution object. Yeah, because this is not a linear equation. Okay? Not a linear equation. Okay, yeah. So for linear equation, that's what we call the linear radial property. All right. Now we have a new solution form, and the capital A, capital B could be arbitrary constant. So here we apply these two freedoms. We have two freedoms, capital A freedom, capital B freedom. Two freedoms, we can use them to make our new solution object satisfy the two initial conditions. All right, so that's the idea. All right, so now let's do the last step of work. Yeah, last step, pretty straightforward. Okay, all right. So let us just, where n equals 0, we have our first equation. For this time, we need to determine capital A, capital B. So we treat them as variables. All right, simple equation. Then, where n equals 1, we have another equation. There, we solve these two equations, so we can get an A number, B number. Then, yeah, so this is A, B number, negative A, right? Yeah, so we can write our final formula. Yeah, yeah, using the golden ratio expression. So we can write out the final formula for our solution sequence. So you can see that's the systematic method to solve linear recurrence relation. Here I spend so much time because I want to emphasize a lot of aspects of problem solving. You can see, so when you need to solve a relatively hard problem, so you need to do a lot of important logical thinking. You need to do a lot of mental analysis work in your understanding. You need to make many different plans based on your understanding, your imagination, your assumptions, your guesses. That's the mental work you need to do. That's the power of human intelligence. So that part is missing in AI. So this valuable part is missing in AI. AI works completely different. AI works dig into large amount of data, doing statistics from large amount of data. That's the power of AI. But they're not inventing rules. AI cannot invent rules. And we can invent a lot of rules. All right. Oh, yeah. So we finish this topic. Next, yeah, we have 20-something minutes. So I want to start our module 4. Yeah, I don't want to waste this 20-something minutes, so we can quite some content. Let me quit this presentation first. All right. Part, yeah, module 4, part 8, insertion sort. All right. The title of module 4, divide and conquer approach. Another important problem solving method, very powerful. So in this module, we will spend a lot of time studying divide and conquer approach. Yeah. So for your midterm, we only cover the first 3 modules. So module 4 belong to the final. Yeah. All right. 8.1, insertion operation. So we solve the same old problem, sort an array, but this time we will use a completely different method. Strategy. We start with a simple case. So when we start, we work on the data with very small sizes. That's very easy to work. Then we grow our data sizes. All right. And every time when we grow, we just increase the size by 1. Add 1 element into our current data, but our current data, we assume it has been sorted. Because you solve the current problem. Then we increase the data size, then we sort it again. Every time when we add a new data item, we sort it. We sort all our data. So that's the idea. Yeah. How to connect 2 adjacent cases. So that's, you have, what's the 2 adjacent cases? The 2 problems with the data sizes difference by 1. That's 2 adjacent cases. Yeah. So here you need to work on the difference part. That is that 1 element part. So your main focus is on that newly added element. All right. Yeah. So let's do some understanding here. When we start, we have a 1 element array. It is sorted already. So we do not need to do any comparison. All right. Then we need to add a new element into this ordered array. Okay? Yeah. You need to do 1 comparison. After 1 comparison, you can put these 2 elements in place. You can sort the current array with these 2 elements. After that, you add another new element, A2. Okay, all right. Then you need to do a few more comparisons to get all 3 elements ordered. That's the process. Okay, all right. The general step. So your current data has been sorted. They are in ascending order, but now you need to add a new element and put it in place. So that's the general way we use to sort all the data. All right. Yeah. So that's our summary. Yeah. All right. So what we're doing, that's what we are doing here. Yeah. And the work we are doing in this way, yeah, we insert an element in a sorted array at the right position. That's the typical work we do here in our sorting, or the main work we do in the sorting. All right. So this step we call it insertion operation. What are we doing? We insert a new element into a currently ordered array. So that's our understanding here. Okay. All right. Yeah. Shift elements for insertion. Now let's look at the details of insertion. When we do it, we need to do a lot of work. So let's look at the detail part. Shift elements to the right. Where you store all the elements of an array in the computer main memory, you use consecutive locations, right? All the array elements must be stored in consecutive locations in the main memory. You cannot change that. So you have to follow that rule. Right. Now, when we do the insertion into the array, you need to preserve the consecutive locations for all the array elements. That structure must be preserved. Okay, all right. In order to maintain that structure, you need to do a lot of element shifts. Yeah. You need to shift certain number of elements to the right to leave space, one location for the new element. All right. The detail, yeah, pretty straightforward. Yeah. Here, we assume the new element, its final location is here. Yeah. So we imagine the detail part first. Because this A sub k, this is the new element. Okay? Yeah. So we can lift it. We can lift it. Put it in a temporary location. Why we lift it? Because we may need to move AK-1 to this location. We need to leave a location for this AK-1. Yeah. There is a possibility we need to do a right shift of AK-1. So that's why we need to leave the original space for AK available. All right. After one comparison, if AK-1 is greater than AK, then we need to make that shift operation, right shift operation. Then another comparison, you may need to do another shift operation, and so on. Yeah. Because here we assume this location is the final correct location. Yeah. So we do all the necessary shifts to the right and then leave the final destination location vacant for AK element. All right, so after all the necessary shifts, this time we can drop that AK element to its destination location. then we complete the insertion. So that's the detailed part of insertion operation. All right. After this step, you complete one round of insertion. But this step, you can apply to all the elements you need to insert in this way. At the end, you will complete sorting. You will get all the elements sorted by insertion way. All right. Number of assignment, because when you do the shifts, you do the assignment operation, right? You do many assignment operations. All right. So here, the assignment operation, big theta of k, on average, because sometimes you need to do more shifts. Sometimes you need to do much fewer shifts. Yeah. But the average is here, big theta of k. Yeah. All right. Next, let's look at implementation of insertion operation. Yeah. Actually, we have seen in the previous insertion step, we have seen it. But this time, we just look at the number of comparisons. Estimate efficiencies. Let's look at all the possible cases. Best case, worst case, and average case here this time. Yeah. Compare and shift operation. Every time we need to do one comparison, then one shift operation, right? Yeah. One comparison, then one shift. Yeah. But the last comparison, then we do not do shift. But we do one assignment operation. All right. So that's the, specific steps we need to do in one insertion step. All right. Then, worst case efficiency. Worst case, each round you need to compare the AK element with all the other elements. All right? Yeah. So, when you complete all the insertions, you need to do this many comparisons. So this number 1/2 times n minus 1. Yeah. All right. That is, if we use asymptotic notation, that's big theta of n squared. Worst case is big theta of n squared. All right. What's the best case? Best case, each round of insertion, after we do the first comparison, then we stop. That's the best case. So each round, we only do one comparison. So you add up all the rounds, we need this many rounds, n minus 1 round. So you total number of comparisons, n minus 1. And for the best case, for what kind of data you have this best case? All right. The data, you need to imagine under what situation you have this best case. So when your data is ordered, so when the data is already ordered, that in that situation you have this best case. Every time you just do one comparison, because your current element is the largest number in your current data part. Current data, largest. So one compressor is enough to make all your data ordered. But you need to do one comparison. You cannot say, yeah, here, some students, I noticed some students say, if the data is already ordered, why you sort it? Right? Some students may argue, if the data is already ordered, why you still sort it? So that's a good question. The reason is even if it's ordered, the computer does not know it. The computer, so it's a hidden fact. The computer does not know the data is ordered. Okay? Yeah. So this ordered data thing, it's a hidden fact. Hidden fact. All right? That's why you have to sort it. You have to apply your sorting algorithm to work on it because it's hidden. Nobody knows it. But it is a fact in a hidden way. So you still need to do some work. Okay, all right. But this one, it is in the big theta of n. You can see it's a huge difference. Worst case in big theta of n squared, but the best case is in big theta of n. The difference is big, so big. Okay? Yeah. So this is an important property. Yeah. So this huge difference, the big difference, it's a big difference. This big difference is important property of insertion sort. Very special property. For other sorts, later after we learn many other sorts, you will see all other sorts do not have this property. This property is quite unique for the insertion sort. And sometimes we need to take advantage of this property. Yeah. All right. Average case, yeah, pretty straightforward. So for the worst case, yeah, because you do all the work from beginning to end, right? Average, you do half of the work, the average. Somewhere in the middle, that's the average. Each insertion step, you take the average. So you do half of the worst case amount of work. The amount of work you need in the worst case. Yeah. So the average case efficiency, half of that amount. Yeah. Half of it. Half of this much. Okay. 1/4 of n squared, but still in big theta of n squared. The average case. Okay. All right. Yeah. All right. Yeah. Yeah. So if you want to do calculation, pretty straightforward. Very easy. Okay. All right. Conclusion. The last part. Because we just observed one property. That property, we want to take advantage of it in some special kind of data. So what kind of data? If the data is almost sorted, sometimes you may have the data like that. Not completely sorted. Some locations, some scattered places, the data is unordered. But the major part of the array, the data is ordered. It's not very common, but it could happen. You know, the data could, with that property, could occur. Yeah. All right. Then, in that situation, insertion sort is best choice you have, because other sorts, you still need to do a lot of work. Later you will see, for other sorts, even if the data is almost sorted, you need to do quite a lot of work. Sometimes when the data is ordered, some sorts, you still need to do the amount of work of the worst case. That's pretty bad, right? Yeah. But the question is, if this property is known, if this property, almost sorted property, if it is known, then you can apply insertion sort. If it's unknown, you cannot apply insertion sort, because there are other better sorts than the insertion sort. Yeah. Here, if I want to use a diagram, so this line segment represents the whole array, but you have a few scattered locations. Yeah. In these red circle part, the data are not ordered. For all the remaining other parts, yeah, data ordered. Yeah. Data ordered, you can see all these parts corresponds to the best case, right? Already ordered, so the best case, big theta of n. So when you do insertion very fast, but in this part, you need to do some work. Okay? But the unordered part, percentage-wise, very small. Think about it. Imagine, percentage-wise, if less than 10%, how about that? Less than 10%. So 90% of the time, you enjoy the performance of the best case. Only in this, less than 10% data part. So you need to do some work. Think about that kind of properties. All right. Yeah. Yeah. So here we finished the insertion sort. Insertion sort is very simple. So we finished the insertion sort. Yeah. All right. But after that, I would like to give you a few examples related to insertion sort. The idea of insertion sort is very simple, but it is useful. It is useful in our problem solving. Yeah. So the next time I will show you how to use the ideas of the insertion sort to solve two examples. I will give you two examples related to the insertion sort. All right. Yeah. So let me stop right here. Yeah. So let's remember, next week we need to prepare for the midterm. Okay. Yeah. So next week. Yeah. So I need to talk about the homework assignment review. So then you will do the midterm, online midterm next week. All right. So that's